This video lecture is on oxidation and reduction reactions. This entire chapter is about reactions in aqueous solution. And this is another situation where we can talk about ionic equations, net ionic equations, and how that works. First thing we're going to look at today are definitions of oxidation and reduction. Oxidation means when an atom or ion loses electrons. And reduction is when an atom or ion gains electrons. Here's something that's helpful as you try to remember that. If you think about it this way, oil stands for oxidation. Oxidation is loss. So when we say something gets oxidized, we are losing electrons. And if you are losing electrons, you are becoming more positive. The opposite of that is rig. Reduction is gain. So rig is reduction is gain. So if you're gaining electrons, you're becoming more negative in this case. So putting that together to remember the difference, always remember oil rig. Oxidation is loss. Reduction is gain. That's really important as we start getting ready to assign oxidation numbers at this point. So as we think about what's happening in this particular picture, calcium is being oxidized because it is losing electrons. Oxygen is being reduced because it is gaining electrons, and then they combine together to form calcium oxide. That's an ionic compound. This is what you did in the lab with magnesium oxide. You did an oxidation-reduction reaction. We thought about it as synthesis, which is true, but this is a more specific type of synthesis called a redox reaction. Oxidation numbers. Oxidation numbers are the way that we keep track of the electrons. It's like a scorecard in baseball or a stat book. You try to keep track of where all the electrons are. We assign oxidation numbers to each element in a neutral compound or charged entity. So how do we do that? If the element itself, if it's in its elemental form, it has an oxidation number of 0. The oxidation number of a monoatomic ion is the same as its charge. For example, if we were to take and look at O2, that's in its elemental form, it would have an oxidation number of 0. If you have something that's monoatomic like sodium ions, we would say it has an oxidation number of 1. This would be an oxidation number of 0. That would be 1 plus. That's in its elemental form. If you have sodium ions, chlorine ions, whatever it is, it's the same as its charge. Don't make this too confusing. Oxidation numbers have a lot to deal with ionic charge. Not totally, but they do have a lot to deal with it. Nonmetals tend to have a negative oxidation number. That makes total sense because they want to gain electrons to get an octet. Some are kind of weird. Oxygen is a -2 unless it's a peroxide ion, which is an O2 polyatomic ion. Hydrogen is a -1 when it's with a metal. It's a +1 when it is with a nonmetal. Some examples of that. When you think about hydrogen being with a metal, if you think about it included, probably easier to look at nonmetals. If you were to look at an acid like HCl, we would say chlorines is a -1 for an oxidation number, and then hydrogen is a +1, like we've talked about the 7 strong acids. If it were bonded to a metal somehow, which is doesn't happen often, it would be a -1. But in this case, when it's with a nonmetal, it would be a +1 when it would be with the acid. Nonmetals are negative. Fluorine is something that never has anything other than -1. It's the most electronegative element on the periodic table. It wants one more electron to complete its outer shell. It's always -1. The halogens in general, that's group 7A, That's fluorine, chlorine, bromine, iodine, and astatine. They're in -1. They can have positive oxidation numbers if they're in oxyanions. Now, if we think about oxyanions, an oxyanion would be like ClO3 1 minus for that polyatomic ion. This is a case where it may have a positive oxidation number. We'll look at more examples of that here in a second. But fluorine is always, always, always a -1. The other halogens, you have to look at the rest of the oxidation numbers. The sum of the oxidation numbers in a neutral compound is 0 if it's neutral. If it's charged, the sum of the polyatomic ions have to equal the charge of the ion whenever we're doing it. We're going to look at some examples of this. This is an example called a displacement reaction. Displacement reactions are sometimes called single replacement reactions because we have a free element replacing another element in a compound. And this is an example of magnesium and hydrochloric acid going through an oxidation-reduction reaction. They show you down here in the bottom of the picture how hydrogen is a +1 oxidation number. Chlorine has to be a -1 because it has to total to be 0. Magnesium is in its free elemental form, so it's a 0. The magnesium replaces the hydrogen. The hydrogen becomes molecular, H2. It's its base form elemental. Chlorine is a -1, and magnesium now becomes the cation with a +2 charge. If that magnesium is more reactive than the element in front of the compound, it will knock it off and replace it. Take a look at it. Magnesium is oxidized because remember, oxidation is lost. It lost 2 electrons. Hydrogen is reduced because reduction is gain. It has gained electrons in this case. Here's an example with copper and silver nitrate, and we're showing the net ionic equation with the nitrate spectators taken out. If we think about all of the oxidation numbers that are happening in this, this copper would have an oxidation number of 0. Silver as an ion has its 1+ oxidation number. Copper has a 2+ oxidation number because it's the same of its charge. Silver is in its elemental form, oxidation number 0. So look what happened to copper. Copper lost electrons. How many electrons did it lose? It lost 2. So oxidation is lost. Copper is oxidized. Silver is going to be reduced. It went from being a positive to having no charge. It's reduced. Oxidation reduction. The copper loses electrons. The silver takes those electrons because the net electrons are always conserved. Check it out. Copper lost 2 electrons. Those 2 electrons went to the 2 silver ions. So this kind of follows along with that rule that the sum of oxidation numbers on both sides has to be the same. It's like creating and destroying matter. You can't do it. The number of electrons lost and gained always has to be equivalent. Now, this will not occur. Copper and silver, if we have copper ions and silver metal, silver will not replace copper. And the reason that happens is silver does not want to lose electrons very readily. It's very stable. So if it doesn't want to readily lose its electrons, it's not going to do the replacement. That's why you see this big X right here. This goes with the activity series, and this is table 4-5 in your book. Be familiar with this. You don't have to memorize it, but be familiar with it. If you look at the top of this table, up here at the top, these elements up here at the top of this, they want to be oxidized. Up here at the top. They have an ease of oxidation. That means they readily want to lose their electrons. Oxidation is loss. You get down here to the bottom, and the farther you go down here, they don't want to be oxidized. There's silver at the bottom. It doesn't want to readily be oxidized. So how do you use this chart? So let's say we've got an element And let's go back to our example of, let's work with our magnesium reacting with our hydrochloric acid. And we want to predict, first of all, will this reaction happen? So when you would go back to that activity series and you would look at magnesium, magnesium is higher up on that activity series than hydrogen. So yes, this reaction will happen. So first step, look at the activity series. Will the free element, will it want to replace the element in the front of that compound? Will it happen? And the answer is yes. Step 2, complete reaction. So on the other side, magnesium is going to replace the hydrogen to make magnesium chloride, and we're going to get hydrogen. Now, when you complete the reaction, you have to write correct formulas. Hydrogen is by itself. It's a Brinkelhoff. It's got to be diatomic. Magnesium and chlorine is ionic. You have to balance the charges, which happen to be the oxidation numbers of it. So when we get finished with this, we have Mg plus HCl arrow MgCl2 plus H2 gas. So once we do that reaction, we know it's going to do the replacing. Now, to identify who's being oxidized and who's being reduced, this is where we use the oxidation numbers. Automatically find the elements that are in their elemental forms. They're not in a compound. They're automatically 0. Remember that when hydrogen is with a nonmetal, it's a +1. Chlorine has to be a 1- because this thing isn't charged, because the net has to be 0. In an ionic compound in general, the oxidation numbers are equal to the ionic charges. Got to balance it. A 2 goes in front of the HCl. So if you identify magnesium, magnesium goes from a 0 to a +2. It has lost electrons. Magnesium is oxidized. Oxidation is lost. Who's been reduced? Let's look at hydrogen. Hydrogen went from a +1 to a 0. Reduction is gain. It's gained electrons. It's not as positive anymore. So it went from a +1 to a 0. Hydrogen is reduced. Again, this is happening in aqueous solution. You can write net ionic equations for this. You would have magnesium as a solid. This is a strong acid, so it would dissociate. This is ionic, so it would dissociate. Hydrogen is a gas, it would not dissociate. And you can write the net ionic equations just like we've done on all the other examples. Now, going back. That happened because here was magnesium on the table. Here's magnesium on the table. Right here. Magnesium's on the table at pretty high. Hydrogen is down lower, so magnesium kicked hydrogen off. Here's another example. Let's say we've got another reaction where we've got fluorine is going to react with NH3. Would this happen? Would we get halogen replacement between fluorine and nitrogen? Would that happen? So if you go back to our activity series, we don't have metals on, we don't have the nonmetals on there. See if you can find fluorine. Fluorine isn't on there. Would fluorine do that replacement? Well, fluorine could do that replacement if we're trying to replace those other halogens. This would not happen because fluorine wants to grab onto its electrons. What if we had another metal, for example, like calcium, reacting with copper 2 nitrate. If you go back to that activity series, calcium would remove it out of the way. So there's a pattern here. As this would happen, the products would become calcium nitrate plus copper metal. Calcium is elemental, 0 oxidation number. Copper is elemental, 0 oxidation number. This is ionic, so they keep the same oxidation numbers as their charges. This is ionic, same oxidation numbers as its charges. So you can tell that calcium goes from a 0 to a +2. It's been oxidized. Copper goes from a +2 to a 0. It's been reduced. Spectator is nitrate. And you can write the net ionic equation. This is a good start for us. Check it out. We'll work the homework problems, take a look at it, and ask any questions that you have in class prior to us going any further. Thanks.